Good morning or afternoon or whatever it is, wherever you are. Um, I'd like to take a look a little bit more on what we're going to be interested in with subspaces. The things that I'd like you to know, one is the definition. Two is the idea. This is supposed to be an old-fashioned light bulb. The idea that A is a subspace means A equals the span of something. So if you could write A as the span of something, then it's a subspace. So this is the key idea here. And this starts us off. Thirdly, then, knowing a subspace means knowing a basis and the dimension and where it is, where it finds home. So maybe this is a two-dimensional subspace in five-dimensional space because it has a basis of two linearly independent vectors. You need to know what a basis is, linearly independent spanning set. But this is the whole deal here. Now, how do the problems look here? What kind of things do you do? I think at the lowest level, I give you the span of some vectors, the span of vectors u1, u2, u3, a bunch of them u4. And all of these u's, u sub I, is in one of the vector spaces, let's say R6. So such a thing is a subspace because it is the span of something, but it doesn't mean you know it. So what you have to do is, first of all, you do know the home, no? This subspace A will lie in six-dimensional space. It can be at most four-dimensional. If these are all linearly independent, then it will be four-dimensional. So it can't span all of R6. You need at least six vectors to do that. But you want to find a basis for it. So finding the basis is often the main issue. And to find a basis, you have two methods. The first method writes these vectors in rows. U1, U2, U3, and U4 are written in rows. Reduced row echelon form. And when you get the reduced row echelon form, it will be stepped. So it'll be something like 1, 0, 3, 0, 0, 1, minus 1, 1, let's see here, 0, 0, 0, 0, and 0, 0, 0, 0. So according to method one, when you row reduce this, if you get this matrix, these two rows tell you two dependencies. Among these U's, there are or rams, among these U vectors, there are two dependencies. So it means that two of these are linear combinations of the others. So you have to discard those if you want a basis. But more than that, it tells you that these vectors right here are a basis. These two vectors, which I wrote as rows, are a basis. So since these are a basis for A is a two-dimensional subspace of R6, and these two vectors, here written as rows, are a basis for it. Anytime you have a stepped collection of vectors, meaning that if you put it in, if you put these as rows of a matrix, except for order, they will be in reduced row echelon form. If you have a stepped basis, it's easy to see that these vectors are linearly independent. So that's method one. Method two is actually the one we started doing. And that puts these vectors in columns. And again, we row reduce. And now you look for the pivots. So maybe we have a pivot here. And I guess these can, this one could have another number here. So these vectors were in R6. So I need 6. 1, 2, 3, 4, 5, 6. 6 components to them. In the last one too, I didn't give enough components. Because I have them in 6-dimensional space. So these are in 6-dimensional space, and we only have 2 pivots. Here's a pivot, and here's a pivot. What does this tell you? This tells you that this is going to be 2-dimensional, and that these 2 vectors are linearly independent. So this time your basis consists of 2 of the original vectors, which can be handy. So in this case, your basis consists of U1 and U3. Again, 2-dimensional subspace of R6. Next easiest, I think, is the next section. Column and row spaces. Of a matrix, M. How do you do this? Well, this one is actually exactly like this. Let me do this by example. Suppose you take M to be this matrix, 1, 2, 4, 0, 1, 3, 1, 3, 7, and let's see, 3, 7, 15. So we look at this matrix and we ask for the column space and the row space for this matrix. What are they? They work the same. So the column space means the span of, you guessed it, the columns of M, and the row space equals the span of the rows of M. And so this problem, once you know this problem becomes like the first problem. And you have 2 ways to do this. You can use either method 1, where you put the vectors that you're interested in into rows, or you can use method 2, where you put the vectors you're interested in into columns. There is an issue here that people run into, and that is you want to, people think they have to put columns into columns to make sense, but these are just tools. Method 1 and method 2 are tools. So if we are looking at the column space and we wanted to use method 1, so method 1 on the column space means you take the vectors that you're interested in, U1, U2, U3, U4, how many you've got, and you put them in rows. And what we're interested in are the columns. So here I put that in a row. So basically I'm looking at the transpose of M. Row reduce. See what you get. If you get a row of zeros, that will mean that there was one dependency among these 3 columns. Now, these are not columns of this matrix, they're columns of M, but that's what we're interested in. And then the remaining 2 will be a basis for the column space. And the same thing goes with finding the row space. And these are the problems that I'll give you for homework, working on row space and column space. And they all work the same. I think in some respects, the hardest one to kind of get your head around, because there's plenty of room for making errors, is finding the kernel and range of a linear transformation. Now, to do this, the first step is to find the matrix rep. So find the matrix representing this linear transformation. I'll call the linear transformation L. But find the matrix representation. Once you do, then it's not too bad if you keep your wits about you. For the kernel, the idea of the kernel is to solve L of x equal to the 0 vector, or solve this matrix equation, or the way you do it is augment M with the zeros, row reduce, you always get zeros at the last column, row reduce, and then these are equations. Because that's what you're doing, is solving equations. So this is actually the key idea. So for example, if the first row here is 1, 0, 1, 3, then that means you have 4 variables and a constant here, x1 through x4 and a constant. So this says x1 equals minus x3 minus 3 x4, and x3 and x4 will be free variables, because otherwise these would have gotten zeroed out if they're not free variables. So the 3 and the 4 are going to be 3 free variables here. So x1 is minus s minus 3t. And then the fact that you have 2 free variables here is going to tell you that you are going to have a 2-dimensional, the kernel will be 2-dimensional. Number of free variables will give you the dimension of the kernel. And you have to do a little arithmetic to find what the basis of the kernel is, but that's what we did last time. So this is the idea of the kernel. The fact that finding the range uses the same process is what's confusing. The range in this case is the span of the columns. Oh yes, so the range is the same as the column space here. So again, you take the same matrix M, you row reduce, but now you treat everything as a vector. Here I'm using method 2 because it uses the same reduction you did for finding the kernel. And then if this becomes 1031, reducing m, this will be a pivot position and will tell you that the first column is one of the elements of your basis. And the other pivots will tell you the same. You can also use method 1 to find the span of the columns. And actually, I would prefer that, but you will have your choice. It's a little extra work if you use method 1 to find the span of the columns. This is the whole thing basically for subspace other than what they look like. What do they look like? One-dimensional is a line. A one-dimensional subspace of R6 means that the home of this thing is R6, but this thing is a line. If you have a two-dimensional subspace, that will be a plane. The basis will have two vectors no matter what space it's in. So you can have a plane in 3 space, in 4 space, in whatever space, as long as the space is larger than 2, larger than or the same as 2. A two-dimensional subspace of the plane is the plane. So there is only one of those. Okay, little summing it up and a little bit of row and column space. I'll give you problems on row and column space, and see you tomorrow.